Have you ever been told something's impossible only to find out the solution was just kind of hiding in plain sight in a place you never even thought to look? Well, today we're going to dive into a corner of mathematics that starts with exactly that, an impossible problem, and somehow ends with the technology that powers our entire world. We're talking about complex numbers, and their story starts with a problem that looks super simple. So where does this all start? Well, like a lot of great stories in math, it begins with an equation that seems to hit a total brick wall. A really simple question that, using all the numbers we know and love, just can't be answered. It all comes down to this little equation right here. X squared plus 1 equals 0. Now, if you try to solve for x, you get stuck. You're basically asking, what number, when you multiply it by itself, gives you -1? I mean, think about it for a second. A positive number times a positive is positive, right? And a negative number times a negative is also positive. So anywhere on that good old number line we learned about in school, from -infinity all the way to positive infinity, there's just no solution. It's a dead end. Or is it? This is where mathematics gets really creative. See, when mathematicians hit a wall, they don't just give up. They build a door. They decided to just invent a solution to this problem, to literally imagine a new kind of number. And the big leap of faith was this. What if we stop trying to find a number that works and we just create one? Let's just define a number that has the exact property we need. This wasn't about discovery. It was an act of pure invention. And here it is. We call it I, the imaginary unit. Its whole reason for existing is defined right there. I is the number whose square is -1. That's it. It's the key that unlocks the problem we couldn't solve. Just by saying this now exists, we've suddenly found an answer to our impossible equation. And this right here is the big aha moment. The reason we couldn't find I on the number line is because it's not there. It exists on a second axis, one that's perpendicular to the first one, an imaginary axis. We've literally gone from a one-dimensional line to a two-dimensional plane. So this new two-dimensional space has a name. It's called the complex plane. And every single point you can imagine on this plane is a unique number, a combination of a real part and an imaginary part. We write these numbers in the form a plus bi. Now, don't let that scare you. The a is just the real part. It tells you how far to go left or right, just like normal. And the b is the imaginary part. It tells you how far to go up or down. That's it. It's basically just a set of coordinates. Now, what's really cool is that adding and subtracting these numbers is super easy. You just add the real parts, add the imaginary parts. Visually, it's kind of like just sliding a point around on the plane. But multiplication? How do you multiply 2 points on a graph? That is where things get really, really elegant. It turns out that multiplication in the complex plane isn't just a dry calculation. It's a geometric action. It's a transformation that involves rotation and sometimes scaling. And this is the core idea right here. Every single time you multiply a number by I, you rotate its position on the plane by exactly 90 degrees counterclockwise. So you start with the number 1, right? Multiply by I, you land on I. Multiply by I again, you land on -1. Do it again, you're at -I. And one more time, you're right back where you started at 1. A full 360-degree trip. Okay, so if multiplication is all about rotation and changing the distance from the center, is our a plus bi coordinate system really the best way to think about it? I mean, it's great for directions, but what if we want to describe the rotation itself more directly? Well, this leads us to another way of writing these numbers called polar form. Instead of giving left, right, and up-down directions like a street grid, polar form gives you a distance from the center, r, and an angle, theta. It's literally like using a compass instead of a map. And as you can probably guess, this compass form is absolutely perfect for describing rotation and scaling, the whole point of complex multiplication. So at this point, you might be thinking, okay, that's pretty neat, rotations are cool, but what is any of this actually for? Well, get this. This supposedly imaginary math is actually the bedrock of modern electrical engineering. You see, when you're dealing with alternating current, the stuff that comes out of your wall socket, things like voltage and current are always changing. They oscillate, and they can get out of sync with each other.
This out-of-syncness is called a phase shift. And it turns out complex numbers are the perfect tool to describe both how big these signals are and what their phase is.
This table just lays it all out perfectly. The total opposition to the current, which is called impedance, isn't just one number. A simple resistor, that's just a real number. But an inductor, that shifts the phase by a positive 90 degrees, a pure positive imaginary number. And capacitor shifts it by negative 90 degrees, a pure negative imaginary number. You see the connection to rotation? It's right there.
And here is the truly beautiful part. To find the total impedance of a whole circuit, you don't need some crazy complicated trigonometry. You just add the complex numbers. So in this example, you take 4 for the resistor, add 3i for the inductor, and subtract 5i for the capacitor. The total impedance is simply 4 minus 2i, an impossible number to solve a very, very real engineering problem. So let's just zoom out for a second. What started as a purely mathematical curiosity, right? A clever trick to solve an equation that had no answer, it turns out to be a fundamental language for describing the physical world around us. And that's really the big takeaway here. Complex numbers aren't imaginary in the sense that they're fake. They are a tool. They're an expansion of our mathematical toolkit that lets us model things like electricity, signal processing, even quantum mechanics, with a kind of precision we just couldn't have otherwise.
This quote from one of our sources really just nails it. The abstract solution to an old algebra puzzle gives us the perfect language to describe how a modern circuit works. The geometry of rotation and the physics of electricity are, in a way, speaking the same language. It's all connected.
And that kind of leaves us with this one last fascinating thought. We solved what seemed like an impossible problem by imagining a whole new dimension of numbers. So it really makes you wonder, what other problems that seem impossible to us today are just waiting for someone to imagine the right kind of solution?